All right. Hi, everyone. Let's get started. My name is Alin. I am the head of cryptography at Aptos Labs. We're a layer 1 network for smart contracts using the Move programming language. Today, I want to tell you about this feature, not just applicable to Aptos blockchain, but also to any other blockchain out there, for building blockchain accounts that are keyless so that you don't have to worry about secret keys, you don't have to worry about mnemonics, you don't have to worry about anything like that if you're novice users. So basically what you're going to do instead is you're going to sign transactions with your Google account, not with your mnemonic. So the kind of idea behind this thing is this question of how could a blockchain account work if we lived in an ideal world, right? So the way I see it is I would go to a web wallet. Here I'm showing you ours, aptosconnect.app. This web wallet would ask me to sign in with Google. I'd select my Google account, I'd sign in, and now I'd have access to my wallet. I could connect it to a DApp, I could do whatever I want. And in fact, it wouldn't have to even be a wallet. It could be a DApp directly that I could sign in. Instead of actually using a wallet, I could even have a promptless UX. So if you get one thing from this talk, it's that your blockchain account is your Google account, right? So that's what a keyless account is. This means that it's as hard to lose as your Google account, it's as secure as your Google account, or really any other OIDC, OpenID Connect account, Facebook, GitHub, and so on. And most importantly, there's no MPC custody, right? So there's no third-party system, or decentralized or not, that we're trusting with your keys. It's literally just Google. There are no secret keys involved, at least none that you have to worry about losing or having them stolen from you. Your Google account is your secret key, is the way to think about this. And it's privacy preserving. This is where the zero knowledge part comes in. This is where Noir comes in. And this is why you guys are here. So it's privacy preserving in two ways. The first way is Google does not learn your blockchain address nor your transaction history. It would be really bad if that were to happen. And the blockchain does not learn your email address, right? It would also be bad if that were to happen because you might not want people to know how much money you have, right? And so why enable this feature? The goal is really to expand safe, seamless access to cryptocurrencies. We want cryptocurrencies in the hands of more people. Most of these people will lose their secret keys if they have to set up one. So how are they to use cryptocurrencies? They'd have to install a wallet. They have to write down this mnemonic. As a result, they're going to lose their account. They have to deal with the transaction prompts. What is a transaction prompt? It's very confusing for novice users. If they want to do this from their phone, their laptop, or their iPad, they're going to run into a lot of difficulty moving over their mnemonic. And again, if they're novice users, they're going to get phished. Like they're going to put their secret keys in some Discord. This happens all the time. So instead, the way things can work is things can be walletless and promptless. You don't need to have a mnemonic. It's very hard to lose your account. As long as you can recover your Google account, you can recover your blockchain account. It's cross-device as long as you can sign in with Google from any device. And you can even get some nice perks, like you can send money straight to an email address. You don't have to type in a 64-character hexadecimal string, right? Now, why not do this? So usually the main objection to not doing such a thing is that people don't trust Google or they don't want to trust Google. And that's fair. And for those people, I would say you should do self-custody, especially if you're a power user. But keep in mind there's been billions of dollars in lost cryptocurrency assets. So not a lot of us are qualified to do self-custody. Or you can do something like 2 out of 3. You can have Google and Apple, and you have 3 total factors. Or you can do kind of minimize the reliance on Google. So instead of trusting Google to sign your transactions all the time, you can trust Google to just help you recover your account, right? So only there's like a really small window in which Google could screw you over and steal your account, right? And I'm happy to talk about that at the end of the talk more, since this is a very genuine, legitimate objection. So basically what this talk is about is how does this feature work? So I want to show you some very simple cryptography, digital signatures, hash functions, zero knowledge proofs. And what I'm hoping to get from this is I hope you guys will take this and implement it in Noir, okay? Because that's what I want to try doing and I need some help. And I also hope you take kind of the paradigm as a whole and consider it for your systems that you're building, because I think it's very, very useful and very, very user-friendly. Okay, so let's begin by kind of going through this sign-in with Google flow that all of you guys are probably familiar. So, we have a user, we have Google, and we have some application which is registered with Google and got this application identifier from Google called the client ID, right? So that it can support the sign-in with Google flow. So the way typically things work is the user goes to the app displays a prompt for the user to sign in, the user selects their Google account, and in this request, the application includes its identifier as a URL parameter. But it also, very importantly, can include any arbitrary data. And this is really key for enabling keyless accounts. I'm going to show you in a few slides why. Right? So keep this in mind. The application, as it signs you into Google, can include any data it wants in there. And so now that the user signed in, if he has a valid cookie and if he typed in the password correctly, Google will send back to the application a digital signature over the following things. So first, there will be one of the signed fields will be the user's email address that's successfully logged in. The other field will be the application's identifier that the user signed in successfully. And the last field is this arbitrary data that the application included, right? And so now, if you look at this, you realize that, well, this application could take this signature, sigma OIDC, and give it to any third party who has Google's public key to verify, right? It's a digital signature. It can be verifiable by anyone. So that's the first observation. The second observation is that this third party can actually be a blockchain, right? Why not? Why can't it be a blockchain? And that the third observation is that the application can be a wallet, like the Aptos Connect wallet that I just showed you, that you sign into. And so it can also be a DApp, like a DeFi app, if you want a walletless experience. And so that's kind of brings me to the last observation, which is that the data that the application includes for Google to sign can be a transaction, right? So now what we've done effectively is, as Alice signed into her wallet, the wallet put a transaction in the arbitrary data, and Google gave a signature back to the wallet over Alice's email, the application's identity, and the transaction, right? And so this is the key idea behind keyless. If you take one thing from this talk, it's kind of this image right here, but we're going to polish it some more because there's a lot of privacy aspects to take care of, right? And one thing I want to mention here is that if this is to work, then the blockchain has to have access to Google's public key, under which it issues signatures, and this public key keeps rotating. And so you actually need to build an on-chain oracle. So this is kind of difficult to do on some blockchains, at least. Right, so put another way, what we have is like the wallet can send a transaction for an address to the blockchain together with the signature from Google, the application's identifier, and the user's identifier, right? And what does the blockchain do? It takes the signature, the user identifier, the application identifier, and the transaction and verifies it against Google's public key, right? So far, so good? OK, great. And of course, like the last thing it has to do is make sure that the address that it wants to execute this transaction for matches the user and the application ID in the signature, right? Well, this is great, but it has really big privacy problems, right? So the data that the wallet has to include for this transaction is Alice's email and the application ID. Maybe the application ID you don't care about, but your email you do care a lot about, right? So how do we hide this? Well, this is kind of our bread and butter here. We're just going to do it via a zero-knowledge proof, right? So instead of giving the signature, the application identifier, and the email address, we're going to give a zero-knowledge proof of knowledge of a signature, application identifier, and email, such that this signature verification passes over the secret data, and the address is derived from the secret data correctly, right? So in effect, what this is doing, it's convincing the blockchain that, hey, for this address, Google with this public key has signed this transaction, right? That's what this is doing. Now, I should say here, it kind of, again, getting back to Noir and to computing zero-knowledge proofs fast, is that this can be kind of slow to compute. So the way we do it on Aptos is we have an external prover service to do this. And kind of writing the ZK relation in a fast enough DSL with a fast enough ZK snark scheme is a really exciting, not only research area, but also engineering challenge. But we're not done yet, so there's kind of a problem here. Like every time you want to sign a transaction, the way I've explained things so far, you'd have to sign into Google, include the transaction as arbitrary data, so that you could get a signature from Google on it. So that's pretty bad from a UX. You don't want to sign in every time, right? So how we're going to solve this? This is kind of trivial. It's every problem in computer science is just add a layer of indirection, right? So instead of signing the transaction, instead of asking Google to sign the transaction, I'm going to ask Google to sign an ephemeral pub key, whose corresponding ephemeral secret key the user knows, right? And the user would have generated this. And it's fine if the user loses this ephemeral secret key, because it can just sign into Google again with a new one and get a new ZKP for it, right? So now, in effect, what the ZKP means is that for this address, the ZKP convinces the validators that transaction signatures can come from the CPK, right? And we kind of have to augment the transaction format to include the signature over the transaction from the corresponding ESK, right? Because now the transaction is not implicitly signed by the ZKP. We have to sign it more explicitly with the ESK, whose EPK is vouched for by the ZKP, right? And lastly, of course, the blockchain has to verify this ephemeral signature, yeah? So this is kind of, we're almost done here. The only problem is that Google sees the CPK. So as a result, when it sees transactions on chain with the same EPK, can tell that alice@gmail.com is signing these transactions. So that's not so good, but that's actually very trivial to solve, right? Actually, this was not going to be the next problem I introduced. I'm going to introduce a different problem before I solve that one. So actually, I should have said, the first problem is that the address, right, is low entropy. It commits to a low entropy email address and a low entropy client ID, which is actually even public. So how do we solve that? We're going to turn this hash into a commitment. We're going to add a high entropy blinding factor in there. We call this blinding factor a pepper, right? Where do you get this pepper from? You get it in our deployment from a pepper service. What if this pepper service gets compromised or hacked? It's okay, it just breaks your privacy. It doesn't break your security. You still need your Google to access your account. The pepper is not enough, right? But how do you authenticate yourself to this pepper service so that other people can't get your pepper? Well, you actually use the same OIDC flow that I've explained so far to convince the pepper service that you are you, and it should give you your pepper, and then you can create the ZKP with the peppers being one of the secret inputs, right? So that takes care of the address privacy, but what about the CPK privacy that I was mentioning before? Well, here the solution is very simple. You can just commit to the EPK using some other blinding factor. This is kind of an ephemeral blinding factor. You don't need to persist it over time, unlike the pepper, which is kind of permanent, right? And so basically, this is the full keyless picture. So if you take a second thing from this talk, it's this image right here. So again, the idea is I'm getting a signature from Google over my email and the application ID and an EPK as a commitment to preserve privacy. Then the blockchain can verify that via the zero-knowledge proof that the address that I'm trying to transact for has the same email and client ID as in this signature from Google. And as a result, the blockchain delegates signing rights from my keyless address to the CPK, and then I can send the transaction signed by that EPK to the blockchain. Yeah? This is a great time to ask questions, by the way, since there's a lot of moving parts here. Yeah?
Okay, so you said they could send to an email address. I'm trying to think.
Great. Yeah, so I can explain that via another slide if you want. The idea will be that I will derive a pepper for you. Instead of relying on a pepper service, I'll put the email in there, and I'll put the application identifier, and then I'm going to send you the pepper.
So even if they haven't gotten the pepper on their
That's
own,
right. I'll just send you the pepper for you, right? Yeah. So that's how that can work. One way it can work. There may be others, but yeah. Okay, so this kind of brings me to how did we implement this keyless ZKP? And one thing I want to stress here is that, as you can see in this picture, the blockchain is doing the ZKP verification, yeah? And so that means that we actually, the slower the verification is, the higher the gas cost of these keyless transactions. So for us, the verification is something that we want to minimize. And so that doesn't give us a lot of options in terms of ZK snarks to use. So we use GROT16, which is the fastest verifier time snark, right, over this BN254 elliptic curve. And we have an implementation in CIRCOM, and I know this is NoirCon, but that's why I'm giving this talk here, because if you want a really tough ZK relation to implement, and actually as a result kind of write some new NoirCon STD libraries, you should take a look at our relation. We have a lot of documentations, and when we have a great CIRCOM implementation that you can use as a reference, and we'd be really happy to collaborate on such an implementation. And it takes about 2,800 lines of code and 1.4 million R1CS constraints for those of you who are familiar with what this means. And as kind of the challenges of doing this efficiently from the prover time perspective, There is the first thing, SHA-2 to 56 hashing. This is a really annoying thing. It takes half of our constraints, right? It's very inefficient to prove SHA-2 to 56. Unfortunately, because of the way Google and other OIDC providers sign messages, we have to use SHA-2 to 56. So we cannot throw Ketchak, we cannot throw Poseidon at the problem. We have to use this hash function. So finding more efficient ways to implement this in R1CS is kind of an open problem. Oftentimes people throw lookup tables at this, but that kind of increases the proof size. So what can we do here? Another challenge, not as big, is we're doing string operations to match the email address in this large message that Google signs, right? And we have to do substring checks and convert strings to integers and so on, all sorts of things. And we have to parse this signed message by Google, which happens to be a JSON web token. And we have to be kind of careful because when we parse, for example, the email field, we have to parse it at the right depth in the JSON. It has to be at depth 0, not at a higher depth where it can be adversarially controlled. So there's some kind of nitty-gritty ways of doing this in a circuit that would be great to optimize. And probably other challenges as well, but these are the first three that seem the biggest to me. So in a future ZKP implementation, again, the consideration is I would start with this technique is meant to secure user funds. So for us, a safety-oriented DSL like Noir is very, very important. The ZKPs that we generate are verified on chain, so the gas cost is proportional to the verifier time and the proof size. And so that doesn't leave us with a lot of options. It could be Grad16, it could be Planck, maybe Marlin, although the proof size is kind of big there. It's really, we just need a new ZK SNARK scheme. This is kind of an open research problem. We're dealing with private information of users. And so in that sense, we'd ideally like to do client-side proving. So we cannot do that with a ZKVM because ZKVM is actually a little bit too slow to prove. And even if it is fast enough to prove, the prove is kind of too big, and then you have to wrap it client-side, and then it becomes slow again. And so once again, this opens a great research problem. What are efficient ZK SNARK schemes that are fast to prove and efficient to verify? And of course, this is an in-production system. We update it, we fix circuit soundness bugs, we fix correctness bugs. We'd like to avoid trusted setups. So again, that leaves us with a few options on the table, Planck or Marlin. And yeah, basically what I'm here to kind of ask you to do is look at our relation, think about implementing it in Noir, and I think it's a great, fascinating thing to work on in this space. And with that said, I want to give acknowledgments to the Aptos keyless team for working on this, the broader Aptos team and Geometry Research who helped us audit the circuit. If you want some developer resources for keyless as well as access to these slides, you can go to my website. I should say there's kind of a shorter URL here that I could have put. And there's a bunch of academic references that I am including here. In fact, like this approach of signing transactions with your Google account was pioneered as early as 2019, as far as I'm aware, in an Ethereum research post. So please take a look at that. So it's kind of surprising that not more blockchains are doing this. So I encourage you to look at it and explore if it's useful for you. And yeah, that's that. Thank you so much. Yeah. Oh, yeah.
I know SUI also has the ZK login.
Yeah.
The functionality from a network's perspective.
That's right.
Lets you log in with Google any kind of Google account.
That's right.
Are you aware of the implementation or any?
Yeah, so both SUI and Aptos, we both, I think, use CIRCOM. As far as I'm aware, the SUI CIRCOM implementation is not open source. It would be great to see kind of what avenue they took. In terms of R1CS constraints, I believe they should be around the same number, but I don't know if yeah. And also, we've taken a slightly different approach to be more open source. So our prover service is open source, our Pepper service is open source, our circuit is open source, and we're trying to get more people to look at this approach and adopt it in their ecosystem. Because if I think cryptocurrency is to be in the hands of most people, for now, not everybody's going to be able to manage their account So as onboarding, I see this as a really good trade-off. Yeah.
Does this mechanism work for like social recovery
Yeah. So the way I've presented it here is as a mechanism to just have an account and sign transactions, right? But with account abstraction, you could do anything you could imagine, right? So you could have these policies of having like a secret key and a Google account, and if you lose your secret key, you can use the Google account to rotate, but only after some lockup expires. And stuff like that. Or you could, if Google is malicious and tries to rotate your secret key, you can use your secret key to undo that. You could do all sorts of things here. And that's, I think, what's really kind of exciting about this is that because we've put everything open source, you could take our code, use it on Ethereum, right? In Ethereum's account abstraction. Yeah. Yeah, and I guess if for those of you who are sort of interested on seeing the full end-to-end flow, there's some slides in the appendix that kind of showcase all of the parties involved here. User, Google, DApp, Prover service, Pepper service, Guardian, and kind of all of the messages flying around, and kind of everything fitting in one slide. Yeah, so I hope that's helpful. Yeah. Yeah, it'll work for any OpenID Connect provider. So GitHub, Apple, Microsoft, anybody that supports OpenID Connect, and that's a lot of providers. Yeah. Auth0, for example. Yeah.
Something related, like you have the key rotation service, like for Google, they use like 256 or something like that.
They use what?
For their like public key, like Google public key that needs to be stored.
Right, it's an RSA public key.
Both
Yeah. So what this? This public key is an RSA public key, and it's published at a URL, and it kind of rotates every 2 weeks, but there's no guarantees. It could rotate every 2 hours. You just don't know. You have to poll it constantly. So what we do is we have custom logic on the Aptos validators to reach consensus on this URL. So this is kind of really crucial, right? Because if somebody can lie to you about what's at that URL, that would be bad. So you wouldn't want to trust one validator, or you wouldn't want to trust one entity to tell you what's at that URL, because that entity can take over your user's account. So what we do is we rely on the whole Aptos validator network to agree at what's at that URL.
And are you tracking like history and like cycle of these keys? Like if Google ever has to revoke a key or something like that? The security guarantees break.
Yeah. I mean, yeah, so what we do is whatever public keys Google publishes, those are the only ones we allow. So if it was PK1, PK2, and now it's just PK1, we ignore PK2. Any OIDC signature with PK2 is useless from our perspective. And any ZKP of an OIDC signature under PK2 is useless, right? And you want to do that because you want to follow Google's lead as quickly as possible and potentially prevent account theft. There's a reason why Google would revoke PK2, right? Yeah.
That's only relevant at the time of creating this app. You're just trusting it.
It's relevant at the time of transacting. The way I'm presenting it here, it's every time you transact, you wrap OIDC signature in a ZKP, right? It so happens that you only need to do that once, and then you can sign with the ephemeral secret key and reuse the same ZKP, right? But at some point, that ZKP will expire, and you'll need to redo it. Because you don't want it to kind of be indefinite. Stuff does get lost from client devices. You do want to give it an expiration date.
So it's like it could expire, and then you trust the public key at the time when it expires, or when the user chooses to renew.
The expiration is orthogonal to the public key issue, right? It's independent. If the public key has changed, then your ZKP becomes invalid automatically because the signature is under an expired pub key. Yeah. So then you would have, the good news is though that it's really easy to re-query Google for a new signature, right? And you rewrap that and you're done. You don't even have to re-sign in, if that makes sense. So for the same message signed under the expired PK2, Google will gladly re-sign it for you under the new PK2 prime or PK3, right? And then you can rewrap that in a ZKP. You're done. The user doesn't notice anything. Yeah. Yeah, there's some, it's very nice that you're asking this because this kind of brings to the forefront some implementation complexities here. It's not exactly easy to take care of all edge cases. Yeah. Yeah.
How's the expiry of EPK is checked? And is there any consequences if those ephemeral publicity does not expire?
Good. Let me start with the last question. So the consequence with the EPK not expiring is if the ZKP pi is leaked from your device, then and an attacker also gets its hands on your ESK, then it has your account, right? So you want to give it an expiration, just like reasonable operational security, I would say, dictates that you make it expire. Now, how do we make it expire? So the EPK is part of the public input to the zero-knowledge proof, right? So here, when I say EPK, I implicitly mean an EPK concatenated with an expiration date. So that means the blockchain validators have access to the expiration date and can check against the current time on chain. Is it expired? So it's pretty straightforward. I'm just not showing it too explicitly here to keep things a little bit more digestible. Yeah. Yeah. Okay. Thank you guys so much. Cheers.